1, 2, 3. Okay, it's working. Okay, so let me start. Today we are going to take a better look, a deeper look at electromagnetic waves. Last week it was sound waves, this week electromagnetic waves. Okay? So, as you probably remember, electromagnetic waves are carried by an electric field which vibrates simultaneously with the magnetic field, okay? And the vibrations of these two fields, they interact with each other. A variation of the magnetic field induces an electric field. A variation of the electric field induces a magnetic field. So these vibrations are coupled, and this is how electromagnetic waves progress, and so they can progress in the vacuum. You don't need any matter support for electromagnetic waves, contrary to sound waves. Sound waves, you know, they propagate. It's a pressure wave, so if you don't have matter, there is no sound which propagates. While with light, you can have electromagnetic waves traveling, light or other electromagnetic waves in vacuum. For instance, the light of the sun arrives to us from the sun through the vacuum of space, and it works very well. Okay? Then it said here, electromagnetic waves are created by the vibration of an electrical charge. Okay, this is something we didn't see yet. It's a phenomenon known as induction. I can show you a small simulation for that. I'm sorry, it's just that I didn't open it before. So if I go to PhET, my beloved simulator, if I go to PhET, we have one simulation of electromagnetic waves that I'm going to show you. It's sound and waves. Okay, and we have this one here, which I wanted to show you. So I have to download it. It's a bit different than the other ones. And now I have to open it here. Okay. This, you see the simulator? You see the window?
Yeah.
Okay. So this illustrates a radio station with an emitting antenna here, emitting antenna. And here it's somebody who listens to the radio. It's a receiving antenna, okay? And this black ball here simulates an electron. It's of course completely wrong. There is not just one electron moving. There are many electrons moving. But basically what happens in the antenna? You have these electric charges moving, and this generates an electromagnetic field. I will therefore make these charges move, and you see it gives you an electromagnetic field. This is probably only the magnetic field that's simulated. This gives you an electromagnetic field, which then propagates through space, and when it arrives on the receiving antenna, it makes the charges in the receiving antenna vibrate, and this generates a very tiny current. And then there is an amplifier which amplifies these currents, which decodes the signal, and you can listen to the radio. Okay, so basically a moving electric charge is going to generate a magnetic field which propagates. Okay, this is a very, very simple way of looking at things. Okay, so the propagation which travels in an electromagnetic field, it's a propagation of the magnetic and the electric fields, and these propagations go at a speed which you should know, which is the speed of light. Do you know the speed of light? Hmm? Yes, how much is it? Hmm? Right. So in more usual units, it's 300,000 kilometers per second. It's not exactly 300,000, it's 299,900 something. So this approximation of 300,000 is a good approximation of the speed of light. Okay, and so it's 300,000 kilometers per second. So it's 300 million meters per second, and 300 million is 3 times 10 to the power 8. It's the value that you have here. Okay, and then there is a relationship which I would like to recall you, which we saw in the beginning of the course. It's this relationship which gives you which states that the velocity of the wave, so in this case the velocity of the light, is equal to the wavelength times the frequency. Okay, this letter nu here, okay, Greek nu, you write it like this. This is a letter we commonly use to describe the frequency of electromagnetic waves. So now I will no longer use the F that we were using before for frequency. I will use nu because this is the standard notation. Do you remember how we derived this equation? We did it in the very beginning of the course. It's an important equation, okay? You know that in general, a velocity, let me write it not in differential form, you know that the velocity is a distance divided by a time, okay? Because the velocities are in meters per second, so it's the distance divided by a time. Now, if we try to apply this equation to a wave, what is the typical distance for a wave? It's the wavelength, okay? It's the length that it takes for the wave to have one complete oscillation. So this is the wavelength, okay? And now by which time should we divide it? Well, the time it takes for the wave to do one complete oscillation is called the period. And we saw that the period is 1 over the frequency, so 1 of the period is equal to the frequency, and this is where this equation comes from. Velocity of the wave is equal to the wavelength times the frequency. It's this equation here, where instead of the velocity here, we have put the velocity of light, which is the velocity of the wave. Okay, so this equation is important and we are going to use it today, right? Now we saw that this I told you, the velocity of light is 300,000 kilometers per second. It's 3 times to the 8 meters per second. But now what you should understand about electromagnetic waves is that the electromagnetic waves, they cover a wide range of phenomena. Okay, and you can classify these phenomena and you can give them specific names according to the frequency or to the wavelength. You see up here we have a scale of frequencies, okay, and this scale goes from 10, I cannot read, sorry, I have to go closer. It's from 10 to the power 0, 10 to the power 2, 10 to the power 4, 10 to the power 6, so this is a logarithmic scale, until 10 to the power 24, okay? This is a huge frequency, 10 to the power 24 hertz. It means that we have 10 to the 24 times a complete cycle in 1 second, okay? And now you can classify this phenomena also according to the wavelength, okay? Because the wavelength and the frequency, they are proportional through this equation. Well, they are inversely proportional, not proportional. So you can also classify all these phenomena with the wavelength. But here, where the frequency was low, the wavelength is high. And where the frequency is high, the wavelength is low. Okay? Let's check this. Let's check that the frequency of 10 to the 24 hertz corresponds to a wavelength of 10 to the minus 16 meters. Let's check it, okay, just to convince ourselves. How could we check that? What do you think? How could we do that? It's your turn now. Allez, speak. Okay? We take this equation, C is equal lambda nu. Okay? So what do you want to start with? Start with the nu. Okay? So if we want to compute lambda, lambda is going to be given by what? This you know. Now this is what we would like to compute. Okay? I'm going to start from this frequency and compute lambda. Okay? So if exactly, it's C over nu. C is 3 times 10 to the 8 in the basic units, meters per second. And nu, the frequency, which you have here, is 10 to the power 24. Okay? So this gives us 3 times 10 to the power 24 minus 8, which is 16 hertz. Okay? So it's not exact, but you also see that this line is not exactly in front of that one. Okay, we have 10 to the minus 16, we have 10 to the minus 14. So indeed, 3 times 10 to the power 16, it's about here. And you see the correspondence between wavelength and frequency. Now, if you want to classify electromagnetic waves according to the frequency or to the wavelength, it's your choice. It's equivalent, okay? Because there is a unique correspondence between frequency and wavelength, right? Imagine here we have a frequency of 1, okay? This is 10 to the power 0, which is 1, okay? What is the wavelength corresponding to the frequency of 1? Well, we saw that the wavelength is c over nu. So it's c, the velocity of light, divided by 1. The velocity of light is 3 times 10 to the power 8. Okay, and you see that here, well, we have 10 to the power 8, 3 times 10 to the power 8 is here. So we checked it in two different places, it works. Okay, so now you can classify your electromagnetic waves according to the frequency, let's say. Okay, so if we start at very low frequencies, and so very long wavelength, we have the radio waves, and it's a certain type of radio waves which we no longer use nowadays. The guys talking to the other side of the earth, les radio amateurs, I don't know how to say that in English, they use this kind of waves. When I was a kid, there were radio stations like Europe 1, which were emitting on long waves, and it's this kind of frequency. So these waves, they behave differently from the other waves. They can follow the terrain because their wavelength is very long, so they're not stopped by mountains. Some of them can be reflected by the clouds, so with these reflections by the clouds you can go further. With these waves, if you are good, you can talk to the other side of the earth in good conditions. Okay, now the waves we have here, they're a bit different. They're higher frequency and smaller wavelength. And here you recognize FM, for instance. Do you know what it means, FM? FM, not FN. Not FN. FM. It means frequency modulation, and this is amplitude modulation. So this is what we call les ondes moyennes in radio, okay? Until like 20, 30 years ago, this was still quite widely used. There was a big emitting station in Switzerland, which was called Sauton. Sauton is a country in Canton de Vaud. And when people were saying that they were listening to the Swiss radio, they would say, oh, j'ai écouté Sauton hier. It was the emitter because you need only one emitter for a whole area. FM is different. FM is what we use nowadays for radio. well, there is also numeric radio digital audio band, but it's always connected to this FM. FM has a higher frequency. Do you have an idea of the frequencies of FM waves? Do you have an FM station that you listen to? You know the frequency? No. Okay. Okay. So, for instance, the Swiss Radio Suisse Romande, they have one station. They have many because these FM waves, they go straight, so they are stopped by mountains. So you need to have more than one emitting station if you want to cover an area. They have one which is at 94.4, but what's the unit here of this frequency? You remember the unit? It's megahertz. Okay, it's 94.4 megahertz. Mega means that we multiply times 10 to the power 6. Okay, so this we could approximate at 100 times 10 to the power 6 hertz. Okay, this I approximate to 100. The mega gives you 10 to the power 6. So that's about 10 to the power 8 hertz. Is it correct? Where is 10 to the power 8 hertz? The frequency is here. 10 to the power 8 is here, right in the middle of the FM band. Okay? So the FM band is around these frequencies. Okay? And these are low frequencies. It's still low frequencies. It's not dangerous. Now there are lots of discussions going on about whether Wi-Fi is dangerous, because Wi-Fi is also in this area, and the GSM signals, the mobile phones, they're also in that area. The mobile phone, it's 900 megahertz. Okay, so it's a bit higher here. It's about here at the beginning of microwaves, and there are lots of people claiming that this is dangerous. Well, we don't know for the moment. I mean, I'm not the type of guy who claims is radio sensitive or whatever. I have a hard time taking seriously the people who say they feel Wi-Fi waves, but okay, some people say they can feel Wi-Fi. The problem is that there has been tests which were done on these people, and they submitted them to waves, and the patient didn't know if there were waves or not, and these people were not at all able to tell whether the waves were on or off. So it's a complicated matter, let's say. One sure thing about these frequencies of the mobile phones, okay, is that they have the capacity to heat up a bit the human body, because you see they are in the microwave area, and microwave are well known to be heating up the stuff. Okay, the microwaves is the same. It's the same microwaves that you have in your microwave oven, and these are used to warm up the food. So something which is here will also warm up a bit. And indeed, if you hold your phone on your ear for some time, you feel that your ear is a bit warm at the end. Maybe you already noticed that. Okay, so it has the capacity to warm up the tissues, but warming up a tissue by a few degrees is not something which is considered dangerous. Yeah? The only thing, well, you see there is blood flowing through the tissue, so the blood takes the heat away, the tissue doesn't stay hot. The only thing that could remain hot is the bone, because there is little blood flowing through the bone, so the bone has a temperature increase when you use medical microwaves, and so there are safety rules which says that the bone should not increase its temperature by more than 2 degrees. 2 degrees. Okay, this is the limits that safety regulations give us, but otherwise I don't think it's dangerous, but there are people who claim it's dangerous. Okay, I don't know. Okay, so you have these radio waves. Do you want to know the difference between FM and AM, or you don't care?
Yes.
Ah, that was sincere. Okay, so, and now you will also understand why the FM signal is much clearer than the AM signal. Okay, FM means frequency modulation. AM is amplitude modulation. Okay, let's imagine we have a signal, some electric signal, corresponding to some music or to some voice or to whatever. Okay, we have an electric signal which is doing something like that. Okay, this is volts with respect to time. This is our electric signal. It's an alternative current. In some places it goes in one direction when V is positive. In other places it goes in the other direction. We didn't do alternative currents in this course because it's way more complicated than continuous currents, but most currents are alternative, which means they go in one direction and in the opposite direction. So the electrons, they go back and forth in the wire, if you want. Okay. Now let's assume I want to encode this audio signal to send it through AM. AM is the old system. It's the one which has been used until like 20, 30 years ago. Okay, so we have this signal which we want to reproduce. I'm going to try to redraw it, kind of. Okay, this is our signal. It's not exact, but it's supposed to be like that. What do we do when we have amplitude modulation? We start having oscillations, of which the envelope gives you the signal. Okay, so if you take the maximum of these oscillations which occur at a higher frequency, we call this la porteuse, l'onde porteuse. If you take the summits, the highest intensity points of this oscillation in red, it gives you the signal that you want to transmit. Amplitude modulation. You reproduce the amplitude with a signal at higher frequency. The problem with this is that if suddenly you have a perturbation, let's assume one motorbike is passing next to you, and this motorbike has an engine which is not protected, so it produces electromagnetic waves, and suddenly you feel in your radio a perturbation which is much higher. Well, the system, your radio, is going to count this as one of the points of the signal, and so you're going to hear in the signal. Okay, so it's not very clean, right? Because any perturbation which comes from the outside sums up with what you have here. If I do frequency modulation, the signal is much cleaner. Why? So let me take this signal here, but let me take just one part of this signal. Okay, let me take something simplified like this. Okay, here I will transform the intensity in frequency. So you see here I have a frequency which is very low. You have an intensity which is very low, and here an intensity which is higher. So I will construct a signal which has the same amplitude all over, but where my signal is higher, the frequency is going to be higher. So in this places, the frequency is going to be higher. Here too is going to be higher. Here too, well, then you have negative, don't worry. And in between, the frequency is going to be different. Okay? So you see, we are now encoding the signal through the frequency. We are encoding the electric signal in the frequency of the signal, which has always the same amplitude. Have I been clear?
Yeah.
Okay, you take the intensity you transform it into frequency, and then your wave has a varying frequency when you emit it. Okay, and then your radio decodes that, retransform the frequency into signal, etc. The advantage here is that if you have a perturbation like this coming from a motorbike which is not well protected, you have it here. It's not going to change anything because the system is not sensitive to the intensity of the signal. The intensity is always the same. So this will just not be read. This will just not be heard. Okay? It's a system which is cleaner in itself because perturbations don't influence it. Okay? That's why FM is a nice quality sound. Okay? Now, of course, the new thing is the DAB, digital audio band. So this is another thing. Okay? You have your signal, the amplitudes correspond to certain values. Let's say we have a value of 10 volts here. This value, we transform it into a binary number. You know what a binary number is? You know? Okay, so 10 binary is 2 to the power 8 plus 2 to the power 3, sorry, plus 2 to the power 1. So this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Okay? 10 in binary numbers is 1010. If you want me to explain you how this works, I can. It has nothing to do with this course, but I can. Okay, basically you write this number as powers of 2. 10, it's 2 to the power 3 plus 0 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0. Okay, and then these coefficients that you have here, sorry, this is 0, excuse me, it's 0 times 2 to the power 0, and this is 1. So these coefficients 0, they form your binary number. Okay, so you decompose your number in powers of 2 rather than in powers of 10. Okay, so this 10, you transform it into a binary number. You transform all the signal into a binary number. You have to decide how many samples you take per second. So if you do sound, you will take 44,000 points of signal within 1 second. You will measure the amplitude of the signal. You will transform into binary numbers, and you will send these binary numbers, and then when the signal is received, it's decoded. Every 44,000 samples represent 1 second, and it's retransformed into an analogic signal. And you can listen to your radio, and this is totally free of parasites because it's numeric, whereas this sometimes you can maybe have some parasites. Okay, so the new thing is the DAB, the digital audio band. Any questions about this? Okay, good. So we have FM, AM. Then we have microwaves. Okay, microwaves, they are centimetric. We also call them sometimes centrimetric waves. You see that the typical wavelength of a microwave is the centimeter. 10 to the minus 2 in meters, it's a centimeter. Okay, so these are waves which are a wavelength which is about a few centimeters. Okay, good. Then if we go up in energy and up in frequency, we find the infrared. Okay, have you heard about the infrared? Yeah, you have heard, but what in your knowledge emits infrared radiation in everyday life, you know? Your remote control, sometimes it emits infrared. By the way, you can try one thing which is amusing. You can go take your infrared device and you can film it with your phone, okay? And you will notice that the camera of the phones, they are sensitive to infrared. So actually, if you film it, if you film your remote and you press on it, if you film the diode which is emitting the infrared, you will see the flash. Whereas with your own eyes, you don't see it. You can try that if you want. Tell me if it works. Okay, so the infrared, you have all kinds of devices producing infrared. Of course, the sun is producing infrared. The sun is producing many of these waves. But if you go to the cafeteria in our school, in the place where the plates are waiting before you take them, before you pass to the cashier, they have infrared lamps on top of the plates to keep them warm, because infrared basically transmits heat by radiation. Okay, there are different ways in which you can transmit heat, and radiation is one of these ways. So the infrared, they warm up, and you have infrared lamps. I can show you that. If you take an infrared bulb, you will need that if you have a reptile, for instance, IR bulb. It's not bad. No, infrared is fine. It's going to keep you warm. You see, you have lamps like that, which are quite common, and these you use for lizards. Because if you have a lizard or a snake which normally lives in a warm place, the lizard and the snakes, they like to lie in a warm place. So you have to put in the terrarium, you have to put one lamp like this. You see, this one is specific for Pogonize, a type of lizard. Okay, they are specific, and you are going to install these. You see, it's here, I guess. You are going to install these lamps in a place in your terrarium, so that the terrarium has one warm place when the snake or the lizard wants to be warm, and a less warm place somewhere else. Okay, so if you have reptiles, you know about these lamps very much. Okay. Okay. Does any of you have a reptile? No. I had a boa a few years ago. It was 1 meter 60 long. It was as big as my arm in the middle, and 2 times it bit me, and I got scared, and I sold it. Poor boa. Now, because I gave it a few mice, these snakes, they like to eat live mouse. So you give them the mouse, you take them out of the terrarium, you give them the mouse, and then you put them back. The problem is that if your hand stinks of mouse, it thinks it's a mouse and is going to attack it. And this is exactly what happened to me. So I didn't like it too much, but it's not dangerous. It's just a bit disgusting because their teeth are very dirty. Okay, let's go. Josephine. It was Josephine, my boa. Okay, now after the infrared, if you go up in frequency or down in wavelength, you go up in energy, you have this very small area which represents the only part of the electromagnetic spectrum. The electromagnetic spectrum is all this. This is the only part which we see. Why do we see only this? Because our eyes have been made, either by the creator or by evolution, have been made to be sensitive only to this type of radiation. Okay, and as far as I know, most animals, they see these same colors. I guess that if you apply the theory of evolution, I guess that possible mutations in which the eye was able to see other frequencies were not really an advantage. So no mutation of the human race able to see more frequencies survived. That's all. So we all see that. Okay, and this drawing, of course, the colors are a bit they are not good because my printer no longer has good colors, but you see you have the different colors, okay? So you have the red, which is here, you have orange, you have yellow, you have green, you have blue, and you have violet here, okay? And these colors come specifically in this order, with the red being lower frequency and higher wavelength, and the violet being higher frequency, lower wavelength. So this bar here is just a magnification of this area. Okay? And now if I show you that with true colors, this I have prepared in my browser somewhere. It's here. Okay, you see the image?
Yes.
Okay, this is basically the same image that I'm showing you. You see on the right that we have radio waves, then we have microwaves, infrared, and here is the visible part. Okay, it's here expanded so that you can see all the colors. You see that we have the red on the right side, the blue and the violet on the left side, and you see that the wavelength here is 750 nanometers, so 750 times 10 to the minus 9 meters. And up here on the other side, it's 400 nanometers. Okay, so the wavelength is shorter for the blue, so the energy is bigger for the blue. The energy is higher. The blue is a bit more energetic than the red. Okay, and you have all the colors in between, the colors of the rainbow, which are there. Right?
Yes.
I explained you how the rainbow is formed. Maybe it's the right moment to explain you again. We studied refraction, and as you may remember, well, we didn't do that in the class really, okay. But if now I take a simulator, so of course I will go to FET, and I will take simulator on refraction, which is, in my opinion, their best simulator. It's this one. Okay, let me start it. So there is one first section that we used until now where we do the refraction, etc., etc. But there is a second section with prisms. Did I show you that?
No.
Okay, so let's suppose now that we have a prism, okay, and we shoot at this prism with a ray of light. This is red light, okay. You see here we have a first refraction. We go from air to glass, so the speed is lower in the glass, so we are going closer to the normal. The normal is like this, you see. Okay, and then here there is a second refraction. The normal is like this, and here we go from a slow medium to a fast medium, so we go away from the normal. Okay, so let me now move this a bit so it's kind of symmetric, and so we can see. I want to see down here what's going on. Okay, we did that with red light, and red light, this is a laser of red light, so all the light is red and it's deviated in the same way. But now what happens if I use white light? Okay, white light contains all the colors of the rainbow. The white is just a mix of all the colors of the rainbow. Okay, if you mix all these colors, you will see white. And the different colors, they don't get deviated in the same way. You see that the red, which is up, gets deviated less, and the violet and the blue, which are down, they get deviated more. Okay, I can show you this like that also. I can change the color. Here I have red, and now I'm going to go towards blue. You see that the deviation is changing. You see it? Okay, so this means that refraction slightly depends on the wavelength. In first approximation, we don't take that into account. We didn't take into account. Okay, but if you want to be more refined, you need to take this into account. And so, due to this, refraction separates the white light into its components, and that's how you get a rainbow. And so where does this refraction happen when you have a rainbow? It happens in the drops of rain which are falling. The drops of rain, you have light going in. This light is refracted inside. It's going to be maybe reflected totally inside a few times before it can go out. So colors are separated, and in the end you see a rainbow in the sky. And the position of the rainbow depends on your position and the position of the sun. So two people in different locations will see rainbows at different places. There's one other thing I want to show you about the rainbow. Yeah, let's take this image. Is there something you find strange on this rainbow, besides the fact that it's a double rainbow, which happens? It's rare to see a double rainbow, but when the phenomenon is really strong, you see it. What do you notice between the two rainbows? Compare them. Exactly. Uh-huh. Ex exactly. The two rainbows, if they happen together, they are inverted. Okay? The second rainbow is the inverse of the first one. You see blue, yellow, red, and here you have red, yellow, blue. Okay? So I encourage you to observe that in nature next time you see a double rainbow, which maybe is going to take some time, but it will happen to you at some point. And so this is something that people didn't always realize. Okay, so there are painters who painted double rainbows and they painted them wrong because they did the two of them similar. I don't know now if I have a painting, rainbow painting. Okay, this is paintings of kids. No, maybe I will not find a double rainbow. Let's try, but I don't want to spend hours on that. Double rainbow painting. Yes. You see, this guy got it wrong. Okay? He didn't observe properly. He took the two rainbows to have the same colors. This one, no, this one is correct. Okay? Blue, yellow, red, red, yellow, blue. This one is fine. This one is correct. This one looks wrong. I'm not sure. Okay? This one also looks wrong, etc. Okay? So you can, this one is correct. Okay, whatever. I just wanted to show you that the rainbows, they were inverted. I honestly, I don't know why the second rainbow is inverted. I never looked into that, and I have the impression that it's not so easy to explain. Okay, so we have light. Okay, after the light, after all these different colors, red, orange, yellow, green, blue, violet, we have the ultraviolet. Well, the infrared is below the red. The ultraviolet is besides the violet. Okay, that's where the names come from. And the ultraviolet, you know it. How do you use it, the ultraviolet? What do you do with the ultraviolet? Hello, hello. What are ultraviolet rays good for? Except for astronomy and stuff like that. Well, they make you tan. Okay, the ultraviolet rays is what gives you a tan. And why? How does the tan happen? These rays penetrate your skin, and inside the skin they change some molecular structure. Now I don't know exactly what they change, but they act on the molecules. They change the structures of some molecules, and this gives you a darker color. Okay, if you stay too long in the sun, you can also get burned. Okay, so light, we are used to it because we need light for our living, but light can kill you. If you if you never had a sun bath in the season, you go to the beach on a hot summer day, you stay on the beach all day long under the sun without moving, you're dead. In the evening, you will be completely burned and you will die. Okay, if you are completely burned on more than half the surface of your body, we cannot save you. You will die. So these rays, they can be dangerous. It's all a question of quantity. Now, the problem for the microwaves and the telephones is that it's small quantities, but we don't know if small quantities are really dangerous. But it seems that no. Well, I don't know. It's a big debate. Now, if you go up in energy, you fall into X-rays. X-rays, what do you know about X-rays? What do we do? What do we use X-rays for? You know it. Hello. Yeah, radiography. Okay. So an X-ray, why do we use X-rays for radiography? Because X-rays, they are in the electromagnetic spectrum rays which have a high energy. The energy is not so high as gamma rays. Gamma rays can kill you. But X-rays, they have enough energy to go across your body. Okay? So when you do an X-ray, what do? You put a plate, a sensitive plate, okay? And then on top of that, you put, I don't know, you put your hand, if you need a radiography of your hand. And then here you have a bulb which emits X-rays, and these X-rays, they are going to go through your hand and they are going to make some image on this plate. Okay, so you are going to see your bones. Okay, you are going to see now the bones. Why are you going to see the bones? Because the bones, they absorb the X-rays in a different way than the soft tissue. Okay, they stop them more because the bones are more dense or something like that. I'm not a specialist in X-rays, but you are going to obtain here an image of what's inside your body because the X-rays, they don't cross the bones and the other things in the same way. Now, for a hand, it might be easy to understand, but now we have a problem if, let's say, if you are lying with your, okay, let's say we want to do a chest X-ray. Okay, you are here, your chest is here, so if it's quite big. The X-ray lamp is here, and so you have the structures which are at different levels, which are projected in the same way on the plate which is down here. What structures do you have? Let's say you have the spine here, and then you have the ribs which come to the front, and then you have the lungs here and the heart in the middle, and the image of all these structures, they are all, you see, for instance, here you will see one piece of this rib and one piece of this rib, and everything will be superposed. So it's a mess. Okay, it's difficult to interpret a radiography because a three-dimensional structure has been projected on a two-dimensional plate, and it's been projected from a central point, not even by parallel rays, but from a central point. Okay, and so there was a big invention in medicine, which is the CT scan. Okay, you know the French word for CT scan? I don't like the French word, okay? Le French word is le scanner. Oh, on va faire un scanner. In English, they say a CT scan. And a CT scan is much better as a word. Do you know what CT means? CT? It means computed tomography. So tomography, I don't know the exact meaning of the word, but tomography means when you are able to reveal the structures of something and to make an image of it, okay? And computed tomography means you need a computer to do that. And indeed, how does it work? The CT scan, this has been developed by a physicist, and he received the Nobel Prize in medicine. I don't remember the name of the guy. And how does it work? Well, you take a patient and you put the patient on a bed. Okay, so I'm drawing again the patient from above with the heart, the lungs, the ribs. Okay, and this patient, you put him in a machine, okay, which is kind of round, and inside these machines you have a number of different sources of X-rays. And so this machine takes this kind of image, a two-dimensional image, but from very different angles. To be honest, I don't know from how many angles. I guess it's between 10 and 100. I'm not sure. Okay. And then all these images, they are linked together by a computer who is able to tell based on the position of some element on one image with respect to where it is on the other image. Then this computer is able to give you the image of the body as it is. It gives you a slice of the body, okay, at the place where you have done all these pictures. And then if you need more slices because you need to investigate something which is long inside the body, then you do this every centimeter or every half centimeter or every 2 centimeters, depending on the size of what you are looking for. Okay? Okay. So this is the CT scan. MRI is something different. MRI, in French, NMR, RMN, résonance magnétique nucléaire. This is another type of scan that is very useful, even more than CT, but it's also more expensive, so they give it to you only if they need. And in French, this was called résonance magnétique nucléaire until a few years ago. And then they changed the name because when the people heard this name, résonance par magnétique nucléaire, they were freaking out and they didn't want to have it because it's nuclear. Okay, so they changed the names and they called it IRM, imagerie par résonance magnétique. They just removed the nuclear. Okay, but basically, what is the system doing? It's complicated. I don't know exactly how it works, and even if I knew, it would be complicated. But basically, this is a system that makes some nuclei of atoms vibrate in a certain way. Okay, and when you have a vibration which is at the same frequency as the frequency you send in, you call that a resonance. Okay, so it's résonance magnétique. It's a magnetic field, a very intense magnetic field with electromagnets all around the machine, and this makes some atomic nuclei vibrate, and you can detect this vibration, and then you have differences between the different tissues, and you can identify the tissues. Okay, and then you have the PET scan also. You know the PET scan. PET scan is a way of doing things in which this is positron emission tomography. A positron is what? It's an anti-electron. It's a positive electron, okay? And so you have this system which emits positive electrons, which you can record, and this is used for instance, to assess the evolution of tumors and stuff like that. It's also a very interesting area. By the way, this is an area of physics which is quite interesting. All the medical physics will have lots of things to do with medicine. Okay, but I'm speaking so much. Now, the last category is the gamma rays. The gamma rays, they cover quite a wide range of energy. So the gamma rays which are here, they're cool. It's okay. They're not going to kill you. If you have a piece of of radioactive material. It's going to emit gamma rays. It's going also to emit alpha rays and beta rays. Alpha rays are 2 protons, 2 neutrons. Beta rays are electrons or anti-electrons, and gamma rays, these are photons. Okay, all this, you can see it as a wave, but you can also see it as a flow of particles, and these particles, we call them the photons, because photo is a root which means light. Okay, so the photons here, they have low energy, here they have very high energy, and so you have some which are not so energetic, they are not going to kill you. Now, if you go close to the heart of a nuclear reactor, it's going to become a bit more critical. It's going to be much more intense, and it can kill you. And then the highest energy gamma rays, we don't have them on Earth. They come from the cosmos. In the cosmos, in the universe, we have certain sources of gamma rays which are extremely intense, like quasars, pulsars, etc. And these gamma rays, when they get to Earth, and it happens, they fortunately disintegrate in the high atmosphere, and they trigger a shower of particles which are coming down to the ground. But these particles, we can live with them, it's okay. How space travel is going to deal with high energy gamma rays, which we also call cosmic rays, this we don't know exactly. And it may be that space travel becomes totally impossible just because of that. Okay? It doesn't seem to be very sure now that when we are going to Mars, we are not going to have a problem with this, because the Earth has a magnetic field which protects us from this shit. But if we go out of that magnetic field, it's going to be a mess. And space is not a very quiet place. There's a lot of radiation in there. Okay. I'm speaking a lot today because also you ask questions, etc. Here I wanted to show you, and this is now not physics with equations, but it's everyday life physics. I wanted to show you the spectrum of emission of some light sources. This is the sun. The sun is a very good light source. You see here you have the red, the yellow, the green, the blue, the violet. Okay? And this line here represents the intensity that is emitted by the sun. So you see that the sun emits pretty much the same intensity in all the colors. Okay? And all these colors together give you white light. Now, if you take an incandescent bulb, so these bulbs with the filament inside, okay, the bulbs we were talking about, but which now are forbidden, you can no longer buy them because they use too much current. If you use a bulb like that, you have much more red than blue. Okay, so this type of light is called a warm light because it gives you warm colors. If you light a room with this, your room will appear more warm. The atmosphere will be nicer because there is more red than blue. Red gives you an impression of warmth. Blue gives you an impression of being cold. And you have examples. You have an example somewhere further in the course. Of course, this is an image I copied and then I printed, so the image is not very, very easy to, the colors are not really good. But you see, if you buy a LED warm white, it's going to contain more red, it's going to look more warm inside. And if you buy a LED cool white, which I encourage you not to do because it's horrible, you will have a white light which is very cold, which contains a lot of blue, and it's not nice. Okay, so just be aware of the fact that in different sources of light you have different spectra. You don't have the same amount of light in all the colors. Okay, look at that, for instance, the neon tube. The neon tube is a mess. Neon tube is the worst light you can find as far as quality of light is concerned. But the advantage of the neon tube is that it doesn't use a lot of electricity, and it's cheap. So all the stores have neon tubes. The problem with this is the spectrum. You see, you have a peak in the blue, a peak in the green, a peak here in the yellow, a peak in the red, in the orange red, and then here you have nothing. Okay, so if you look at some piece of clothing that you find in a store and you look at it, you don't like the color, well, take the cloth and go outside, go next to a window, because inside the store you don't see the real color of your clothing. Okay, if you take red pants, well, they will look much less red because they receive less red lights. And if pants are red, it's because they reflect red light. So if they receive less red light, they will reflect less, and you will not see them in the same color. Okay? The LED lamp is better. Okay? The LED lamp has a spectrum which is much more continuous, much more full than this spectrum. Okay? But you see that it has a hole in the green. Okay? It has a hole in the green. So this is, I guess, a warm LED. It's not bad as a spectrum, but again, depending on what you want to do with that, you should be careful. If you want to use lighting for an aquarium with sea fishes, for instance, you need to be very careful about the quality of light. And because the fish and the corals, mainly the corals, they need the right type of light. Okay, so if you do a light for an aquarium, you will use LEDs, but you will put a mix of red LEDs and maybe blue LEDs a bit, depends on the maker, and then maybe some green LEDs or yellow LEDs or whatever. Okay, the blue LEDs, they earn the Nobel Prize. I'm very upset about that because this is technology, this is not physics, but whatever. The Japanese guy who developed the blue LED, he got the Nobel Prize. Okay, because it's difficult to make blue. Okay, so you will make a mix of colors so that your fishes, they have the right light spectrum. Now I want to ask you a question about this. Do you think this is a good light for a plant? It's not an easy question. Okay, this has a hole in the green. Do you think it's a good light for a plant? Let's keep the why yes. Tell me why. It's correct. It's correct. But okay, you give the correct answer now. I cannot bother the others. It's absolutely correct. Okay, you did that at the sick. You have a source of light, and the source of light is sending out different colors. Okay, so I have only 3 colors here, but I think it should be enough. I'm going to do it like this. So the source of light is sending out all the colors from the spectrum. Okay, let's say it's the sun or it's a bulb. Okay, and here you have some type of plant. The plant is green. Okay, I'm going to take a plant without flower because the flower is another problem if it's not green. Okay, I just take the green part of the plant. Why is this plant green? Why is it green? Why do we see it green? Okay, let's assume our eye is here. We look at this plant, the plant appears green. Why does it appear green? Because the plant is reflecting the green light. Okay, the green light which arrives here is reflected by the plant, while the blue light and the red light, they are absorbed by the plant. Okay, so the green light does not go into the plant. The green light is reflected, it arrives to our eye, so the plant does not absorb green light. So if you light up a plant with green light only, it's going to die. Okay? It's going to die because the plant doesn't receive any light. If you want to make a plant happy, give it red, give it blue, give it yellow, give it whatever, violet, but don't give it green because it's useless. So this spectrum here is perfectly compatible with the plant, as you said. Who was it? I don't know. It's Luna. Aha, yeah. So this type of lamp is perfect for a plant because you don't have green, but you don't care. Okay, you don't need green. Well, maybe your plant will look a bit different. It will look less green than before because you send it less green, but it's going to be good for the plant. Okay, and now you have other type of lamps, so fluo compact. I don't know exactly how this works, but you see you have this crazy spectra with peaks, and so these are not good lights for live plants or animals. Okay, and of course the best one is sunlight. And if you need good light for something, it's going to be expensive because you're going to have to mimic the sun. The LED is not a bad way of doing it. And then you can maybe assemble different types of LEDs. Okay. Well, listen, okay. Now about the eye, I just wanted to tell you a few things about the eye. Maybe you know all that already. I don't know. The eye is an optical system. It has one lens, which is they call it lens in English. Okay, le cristallin in French. Okay, and there is another lens, which is the cornea. Of course, the cornea has an effect on the light because it's bent. So if you have a ray of light which arrives, well, let's assume this drawing is okay from the point of view of shapes, okay? And let's assume we have a ray of light which is arriving, it's arriving, let's say, like this, okay? Where does it go? We know refraction, now we can kind of compute that, okay? Here we draw the normal, we go from air into an aqueous medium. So here the velocity of light, it's basically water, it's going to be lower. So we are going to go closer to the normal, okay? And then here there is this lens which has a shape. So again, there will be a refraction here. So I don't know the index of refraction of the crystalline. I have no idea. Okay, so here there will be some refraction. At the other end of the crystalline, there will be some refraction. Here inside the eye, basically it's water. And so the rays, they're going to form a spot on the back of the eye. And in a good situation, you will have the image focused on the back of the eye. And if you have the image of something here, it's going to be projected in the opposite direction on the back of the eye. Okay, so on the back of the eye, everything is upside down. You remember that the images, the real images, this is a real image because we have light arriving here. You remember that the real images constructed with a convergent lens, and here we have a convergent lens. They are inverted. So here indeed we have an image which is inverted, and then the brain puts it back in the right position. We don't notice it. Okay, we are used to seeing things in the right direction. And then in the back of the eyes you have these cells which are sensitive to light. You have two types of cells. You have the rods and the cones, okay? The rods are these things here, these long things, okay? Les bâtonnets in French. These are very sensitive, but they are not sensitive to frequency. So that means they can see only in black and white, but they have a high sensitivity. So this is what you use at night. And since they are not sensitive to colors, only to the intensity of light, at night you see in black and white. Okay, you have noticed that already. At night you don't see the colors if the light is very low, and this is why we say la nuit tous les chats sont gris. Indeed, at night you see shades of gray. And these other cells, they're called the cones. These are sensitive to frequency, so they can see colors, but they work only with a certain amount of light, so you can use them during the day and you can see the colors. Okay? Okay, I've been speaking a lot. Maybe I would stop now, or you want to continue? One thing I wanted to tell you about is the black body. So there is this notion in physics of a black body. What is a black body? It's a body which is usually black, indeed. And why is it black? Because we want an object, a black body, to absorb all the radiation that is sent to him. So he has to absorb everything. So black absorbs all the colors. Okay, black absorbs all the colors. That's the reason why you see it black, because it's not reflecting any of the colors. Okay, so it's absorbing all the energy from the light it receives at different colors, and when it receives this energy, it will increase its temperature. You know very well that if you leave a black car on a parking lot in the summer, it's going to become horribly warm, much warmer than a white car. Why is that? You know that? Why does? Yeah, the white car, exactly. The white car reflects all the light. Well, it's still going to get warm, but much less than a black car. I've had a black car for years, I can tell you. It's horrible in the summer. Okay? And so a black body which receives electromagnetic radiation is going to warm up. And when a body gets warm, it means the agitation of the electrons of the molecules inside is going to increase. If you increase the agitation of the electrons of electric charges, this causes an emission of electromagnetic radiation. Okay, so the black body stores all the energy it receives, and it sends out electromagnetic radiation, which depends only on its temperature. Okay, so a black body at a temperature of 6,000 degrees is typically the sun. Okay, the sun at 6,000 degrees has a certain color which is around white yellow. Okay, and from here comes the notion of temperature of color. The temperature of color is the temperature of a black body who emits that color. Okay, so if you want a black body to emit the same color as the sun, you need this black body to be at a temperature of 5,785, let's say 6,000 degrees. Okay, so we say that the color temperature of the sun is 6,000 degrees Kelvin. It's approximately the same as the surface temperature of the sun. But now if you take a neon, okay, a neon tube, it's a bit more blue, so the color temperature is a bit smaller, like 5,000, but the temperature of the neon itself is a few tenths of degrees Celsius. Okay, so the temperature of the object and the color temperature are two notions which are completely different. And when talking about color temperature, this is important nowadays for LEDs. If you take warm white, you have a color temperature which is low, so which is closer to the red. If you have neutral white, it's average, and if you have cold white, it's a temperature of the order of 5,000 kelvins, and this gives you a light which is very blue, very, very cold, very horrible. Okay? Voila. I will finish here. We have some exercises, but maybe we can do that next week. exercises where we deal with wavelength and frequencies and so on. Maybe you can try, okay, for next week. Next week is going to be the 19th of May. Try to do these exercises if you want. They're not difficult. Again, you have to use this equation C is equal to lambda nu. Sorry, I was not centered. Okay, and you can compute these things. Okay? Do you have other questions? Okay, it's a class in which I didn't do exercises because there are not many. Well, we could have done that, but is it okay for you? You could follow. Ça va? You learned something? Okay, okay, good. Okay, so see you next week, and I will put the video online if you want to watch it again, or for those who were not here. And yeah, have a good week. Bye bye. Bye bye. Bye bye.